Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, Lesson 10, Building Logarithmic Tables. Classwork opening exercise. It says to find the value of the following expressions without using a calculator. Okay, so pause the video, see if you can do this, and then come back and we'll take a look. Okay, so here we go. What power of 10, base 10, will give us 1,000? That's what that means. What power base 10 will give us 1,000? Well, 10 to the 1 is 10. 10 squared is 100, and 10 cubed is 1,000. So your power in base 10 tells us how many zeros there are. So there are 3 zeros here. So what power of base 10 will give us 1,000? And the answer is 3. What power of base 10 will give us 100? There are 2 zeros. It's 2. 10 squared is 100. What power of base 10 will give us 10? 10 to the 1. What power of base 10 will give us 1? Anything to the power of 0 is 1. What power of base 10 will give us 1/10? Remember, if we have to take a reciprocal, we have to negate. So it's a -1 because the 10s are equal. Here we have a 100. So I know it's 10 squared will give me 100, and a negative will take its reciprocal. Okay. And then when we continue off to the right here, now it says the log base 10 of 1,000 equals. Well, that means 10 to the what power gives us 1,000, and it's 3. So what they're trying to solidify here from the prior lessons, lesson 9 and 8, is that what power base 10 will give us 1,000 is the same as saying the log. So instead of saying what power now, it's just going to switch to the log. So the log base 10 of 100, there's 2 zeros. That's a power of 2. The log base 10 of 10 is 1. The log base 10 of 1 is 0. The log base 10 of 1/10 is -1. And the log base 10 of 1/100th is -2. And notice that these are all equivalent. So we're now switching from saying what power of 10 of base 10 will give us 1,000. We say the log of base 10 of 1,000 equals 3. So it says formulate a rule based on the results above. If k is an integer, then the log base 10 of 10 to the k equals what? Okay, so what they're saying is if we take log base 10 of 10 to the k equals something, so we say the base to some power equals 10 to the k, right? Because the base to the power of our answer gives us this value. So I can rewrite it as an exponential equation, and my bases are equal, so therefore my exponents must be equal. So the answer is k. Okay, page 2 brings us to example 1, and it's showing a picture of Earth, and there are 2 stars. So what it says in the manual, it says, suppose that you are an astronomer and you measure the distance to a star as, what number is that? Thousands, millions, billions, trillions, 100 trillion miles away. A second star is collinear, meaning on the same straight line as this is depicting, with the first star and Earth, and is 1,000,000 times farther away from Earth than the first star, as shown in this diagram. How many miles is the second star from Earth? And notice that this is not drawn to scale. So here's what we're going to do. If this star is, let's see, 100, 1,000, million, billion, trillion, is 100 trillion miles away. Okay, is that right? Yes. And this one is 1,000,000 times farther. then it's times, okay? The key word here is million times farther, so we're multiplying. And when we multiply things that end in zeros, what we're doing is adding zeros on to the existing. So I'm going to add 6 zeros to trillion. So it's going to look like this. Okay, this was our original number. 1, 2, 3, 4, and then the 2, and then we're going to add 6 more. So this is hundreds, thousands, millions, billions, trillions, quadrillions, and this is quintillion. Okay, so this is 100 quintillion miles from Earth, since it's 100 times, 1 million times further than this one. Okay. Okay, so how did we do this? We added the zeros up. When you're multiplying by multiples of 10, you just add zeros on, okay? So another way we could have done this is represent this as base 10. So I could say 10 to the 3, 6, 9, 12, 14. Okay, and this number is 10 to the 6. And when we multiply and the bases are the same, the rule is to add the exponents. So this would equal 10 to the 20th. So this is 3, 6, 9, 12, 15, 18, 19, 20 zeros. Okay, that's another way to do it. So how are the exponents related? You take the 14 exponents plus the 16, or 6 exponents, 14 plus 6, and we get 20. Okay, and we're leading up to something here. So the exercise that follows, it says, find 2 consecutive powers of 10 so that 30 is between them. That is, find an integer exponent k. Do you remember what an integer is? We want an integer exponent k. We don't want decimals. Okay, so that 10 to the power of k is less than 30, and 30 is less than 10 to the power of k plus 1. Okay, so pause the video, see if you can do these 4 problems, and then come back and see how you did. Okay, so here we go. To do number 1, keep in mind what 10 to the power of an integer means. So what is 10 to the 1? Well, 10 to the 1 is 10. And 10 is less than 30. And 10 to the, if k was 1, then k is 1 here. What's 1 plus 1? It's 2. And 10 squared is 100. So we know 30 is between 10 and 100. And therefore, we know that k is going to be the power of k has to be 1. Find an integer exponent k so that it's integer exponent. So what does k equal? K must equal 1 because 10 to the 1 is 10. And 10 or 100 is 10 squared. And 1 plus 1 is 2. And this is 1. Okay, so it satisfies that equation. So number 2 says, from your result in exercise 1, the log of 30 is between which 2 integers? Okay, well, since 30 is some power of 10 between 1 and 2, that's what we got from here, then the log of 30 has to be between those powers. So we would say the log of 30 is between 1 and 2. Okay, because our powers are what the log of something equals. All right, number 3, find a number k to 1 decimal place. So now we're getting more precise. All right, so in this case, I'll bring in the calculator. So it says find a number k to 1 decimal place so that 10 to the power of k is between, or 30 is between 10 to the power of k and 10 to the power of k plus 1/10. And use that to find the under and over estimates for log 30. Okay, so if I take 10 to the 1, it's obviously 10. If I take 10 to the 1.1, it's 12.58. Okay. So what we're doing here is we're going to keep going until we find a number that is between, one's less than 30, one's more than 30. 12 is less than 30, so I'm going to keep going. So I'm going to go 10 to the power of 1.2, and I get 15, still less than 30. And then I'm going to do 10 to the power of 1.3, and that's 19, still less than 30. So I'm going to do 10 to the power of 1.4, and that's 25. And we're getting closer. And then I do 10 to the power of 1.5, and that gives me a number greater than 30. So now I know, going out one decimal place, that 30 is between 1.4 and 1.5. Okay, and that we would say 10 to the power of, I suppose I should say. 30 is between 10 to the power of 1.4 and 1.5. So therefore, we can conclude that the log of 30 is between those powers. Okay. Number 4 says, find a number k to 2 decimal places so that 30 is between those, and use that to find the under over estimates for log 30. So we're getting more accurate. Here's what they're doing. So I know it's 1.4 something. 1.5 was too many. So we'll start with 10 to the power of 1.4. And I like going in the middle. And if I'm over, then I can cut my number line in half instead of checking all 10. So I'm going to start out with 1.45 in the middle. And that's still not 30. So I just cut out 1.4, 1, 2, 3, and 4 without having to type a whole bunch of stuff in. So now I know that 1.45 is still less than 30. So I'm going to try to do 10 to the 1.46. And that's still less than 30. 10 to the 1.47. Still less than 30. 10 to the 1.48. And that's more than 30. So now I know that 30 is greater than 1.47, but it's less than 1.48. And therefore, or I should say 10 to the power of, I keep forgetting that. 30 is not less than 1.48. It's less than 10 to the power of 1.48. And therefore, the power is going to be less than and greater than the log of 30. So now I know, oops, that's 48. So now I know the log of 30 is between 1.47 and 1.48. So we're getting more accurate. We could keep going out multiple decimal places to get more precise. Okay, so what I haven't done though is when I'm done is there's an approximation. So in this one here, I could now say K is approximately, make sure you use the approximate symbol because logarithms are generally irrational numbers. They go on forever and ever. So the log of, so K is approximately 1.4. You don't want to do the over, you want to do the under. So in this problem here, now we're getting closer, our approximation is getting better, but it's still not equal. We would say K is approximately 1.47. Okay, so problem number 3, or 4, I mean, on page 3, got us to 2 decimal places. Now number 5 says to repeat this process to approximate the value of log of 30 to 4 decimal places. So what I'm going to do now is do 10 to the power of 1.47. That was our 2 decimal place approximation. 1.48 was over. So now I'm going to go to halfway, which is 1.475, and hit enter. That is still below 30, so I know it's at least 1.475, so I'm going to keep going. So it's 10 to the power of 1.476. And that's still less than 30. So 10 to the power of 1.477 is still less than 30. 10 to the power of 1.478, and that's too many. So now I know I'm going to write this. It's going to be the log of 30 is now, I know, to 3 decimal places is less than or is greater than 1.477, but less than 1.478. So now I'm going to continue with 1.477 and expand out to the 10,000th position. So it's 10 to the power of 1.477, and I'm going to start in the middle, 5, and that's too much. So I'm going to go reduce 10 to the power of 1.4774. That's still too much. 10 to the power of 1.4773. That's still too much. 10 to the power of 1.4772. And 10 to the power of 1.4771. So if I started at the beginning, I would have gotten it on the first two. So 1.4772 is too much. So we're going, the 4th decimal place is this. So now I can conclude that the log of 30 is greater than 1.4772, or 1, I mean, but less than 1.477. So therefore, in this case, that would be log base 10 of 30 equals k, then our k approximation would be 1.4771. Okay. Now number 6 says to verify your result on your calculator using the log button. So if you look here, right next to the 7 is the word log. So instead of trying to approximate this, if you have a graphing calculator, I use, I'm familiar with the Texas Instruments one. I guess the Inspire is probably even better, but I have not used that yet. I haven't learned that. So if I just hit the button log, and I want to know what the log of 30 is, and hit enter, all right, it does it for me. And as you can see, 1.4771, this 2 would truncate, and that's what we have as our 4-digit approximation. So we did verify. Number 7. Now it says to use your calculator to complete the following table, round the logarithms to 4 decimal places. So if x is 1, I want to take the log of x. So if I do log of 1, now I just want to point something out to you here. You should always close your parentheses if there's something following, but if nothing follows, it's not necessary. So I'd always just leave that parenthesis open. It's just quicker, one less keystroke, and the log of 1 is 0. Okay. And the log of 2 is 4 decimal places is going to be 0.3010. Always look to the 5th position, and if it's 5 or more, round up. If it's not, truncate. All right, log of 3, enter. I'll do a couple of them so I don't have to go back and forth. Log of 4, enter. And one more, log of 5, enter. So 3 was 0.4771. 4 is 0.6021, and 5 is 0.6990. So in this one, the 7 made the 9 a 10, 9 makes the, that's 9. Okay, so rounding up. So we're going to continue this process, but I'm not going to do this on screen. I'll just come back when it's full. Okay, so here we go. There it is. This is the log of the values that we were asked to find. So let's look at something here. Log of 10 to the 10 is 1. Log of 100 is 2. And then log of 1000 would be 3. So as you can see, numbers 1 through 9 are less than 1. Numbers 20 up to 99 would be less than 2. And numbers 101 all the way up to 999.9999 would be less than 3. Okay, so every time you go out a multiple of 10, you're going to have a number outside in front of the decimal. Okay, and that's the number of zeros in the log you're taking, as you can see. 0, there's 1, there's no zeros here, 0. 1 0 1, 2 zeros, 2 point something. So look for these types of patterns when you're doing math. And number 8 says, what patterns can you see in the table from exercise 7 as x is multiplied by 10? Write a pattern using the logarithmic notation. So now we want to write that pattern. Okay, so I could say I found the patterns of log of 10 times x to equal 1 plus the log of x. Okay, and the log of 100x to be 2 plus the log of x. I also noticed that the log of 100x equals 1 plus the log of 10x. So those are different ways you can look at what that really means. So we can break it down. So the log of, so what they're trying to say is I found the patterns of log of 10x to be 1 plus the log of x. So what this is 1 plus the log we got over here. 2 plus the log we got over here. So this is leading up to something. All right, page 4 brings us to number 9, and it says, what pattern would you expect to find for the log of 1000x? Make a conjecture and test it to see whether or not it appears to be valid. All right, so here we go. Okay, so it would appear, I guess that the values of log of 1000x will start with a 3 because there are 3 zeros in 1000. That is, the log of 1000x would be 3 plus the log of x. This appears to be the case since log of 2000 equals 3.3010. Log of 5000 is approximately 3.6990. And log of 8000 is approximately 3.9031. Okay, so that's what the solutions here is basically saying. If I take the log of 2000, okay, 3 zeros, it's 3 point something. All right, log of 5000, log of 8000. So if I take the log of 8000, that's 800. So notice that the decimal value, the ones position is a 2 because there are 2 zeros. That was a mistype. Try 8000 is 3.9031, like they said here. Okay, number 10 says to use the results from exercises 8 and 9 to make a conjecture about the value of log of 10 to the power of k times x for any positive integer k. So what we would say here is that it would appear that the log of 10 to the k times x equals k plus the log of x for any positive integer k. All right, so now it says to use your calculator to complete the following table. Round the logarithms to 4 decimal places. So here we go. I'll do the first few. Log of 1 is 0. Log of 2 is 0.3010. So I'll write those. Log of 1, 0. Log of 2, 0.3010. Log of 3 is 0.4771. And I should have a 0 out in front in my ones position just to solidify the fact that there are no zeros in these numbers. So the ones position is 0. Now, if I go out to 0.1, what's going to happen? Now we're doing logs of numbers between 0 and 1. Remember, we can't, the log of 0 is 1, or log of 1 is 0, and we can't take logs of negative numbers. And just for kicks, what's the log of 0? Can't do that either, okay? So what is the log of 0.1? And it is -1. The log of 0.2 is -0.6990. Okay, the log of 0.3 is negative point, I'll say 0 point. I want you to understand that the ones position is 0, -0.5229. So notice what's going on here. As my decimal tenth position gets larger, the number's getting smaller, right? 0.1, 0.9 is greater than 0.1. These numbers are getting bigger, but the log is getting closer to 0 from the negative side. These are also getting bigger. So now I'm going to go out to log of 1/100th. So the log of 0.01 is -2. The log of 0.02 is -1.6990. So the log of, did I do that first one right? The log of 2 is 0.30. Yes. Okay. Now let's do the log of 0.03. And the log of 0.03 is -1.5229. Okay, so I'm going to continue this and fill in this table. Okay, so notice what's going on here. These values after the decimal are all the same as the log of 0.1, 0.01. Moving the decimal to the right just changes the ones position. 1 0 after the decimals, a -1. No zeros after the decimals, a 0. So the log of 0.002 should be -2.6990. So let's check that. So the log of 0.002 is -2.6990. So now it says, what patterns do you see in the table from exercise 11? Write them using logarithmic notation. Okay, so what you can say here is, I found the patterns of log of x minus the log of x over 10. In other words, -1/10 to equal 1. Okay, where's 1? Which can be written as log of x over 10, which equals -1. So they're talking about right here. Okay, plus the log of x, -1 plus the log of x. And log of x over 100 equals -2 plus log of x. So x over 100 is right here. That equals -2 times the log of x. Well, the log of x is 0, so this is -1 plus 0, and this is -2 plus 0. Okay, these numbers are not the same, but after we get beyond these numbers, when we start doing the decimals, 0.2 becomes a -0.6990, and then if I add zeros from now on and make the number smaller by a multiple of -10 to the -1 or -2 or -3, the power is going to be your ones position. All right, page 5 brings us to number 13. So now it says, what pattern would you expect to find for log of x over 1,000? Make a conjecture and test it to see whether or not it appears to be valid. Okay, so here's the conjecture. Let me move this down out from behind me. And it says, I would guess that the values of log of x over 1000 will start at -2 and the log of x over 1000 equals -3 plus some log of x. This appears to be the case since log of, so there's our examples. So the log of 0.002 is -2.6990 and -2.6990 is -3 plus that number we got in our first column up there. Remember that number. Okay, and that's why that number was different. It's -3 plus that gives us this fraction to get us on the other side of 0, and then it stays the same after that. So the log of 0.005 is approximately -2.3010, and -2.3010 is equal to -3 plus 0.6990. And the log of 0.008 is approximately -2.0969. And that number is equal to -3 plus what we got in our first column of our table. So that's what they're looking at, is these values here, plus a -1, plus a -2, plus a -3, and so on. Okay. And now number 14 says to combine your results from exercise 10 through 12 and make a conjecture about the value of the logarithm for a multiple of a power of 10. That is, find the formula for log of 10 to the power of k times some x for any integer k. So that would appear to be that the log of 10 to the k times x equals k plus the log of x. All right, for any integer k. Okay, page 6 brings us to the end of lesson 2. Review the lesson summary and go do your problem set.